Yes, we're here to talk about energy savings and demand reduction benefits with building materials that have high thermal mass. So specifically, we're looking at the compressed earth blocks that I make here in Colorado, and also a partner of mine that makes a phase change material blanket. And so this science work got me out into a program with the National Lab here in Golden through an entrepreneurship program called Westgate. So I've been funded for a couple of years and to do an energy model and some other life cycle assessment studies with the national lab here. So I've been very grateful for the last 2 years being supported by the Department of Energy with this work. And now to really share, because we're about to hopefully finish our paper and have it published in an impact journal. So that's kind of the stage that we're at now. Some of you might know me under as Colorado Earth, and I've gone through a rebranding change to Nova Terra, really with the purpose of reaching a larger audience beyond Colorado and into other regions. Blocks are being shipped to other states even currently, so just using that forward. And I'll give a quick introduction to myself, and then I have Sajith here beside me with the lab who will be presenting also on some of the data. I'm a civil engineer. I studied civil engineering, and then I went to school for architecture in New Zealand after that. And this was the early 2000s. And there I was exposed to mud bricks. So basically a builder who was building mud brick homes. New Zealand has some of the best earth building codes written in the world, actually. They address seismic concerns. They address the wet climate that they have. And so that was a great training ground for me. I was there for about 4 or 5 years and built houses with as a design build team throughout the North Island of New Zealand. One thing that I didn't get exposed to there was cold climate as much because we were mainly building in the North Island. And so coming to Colorado and starting up a facility here and now addressing, freeze thaw and cold climate and insulating the walls has been a huge kind of leap and step forward with the building material and bringing it forward throughout this climate zone. So Sajith, I'll let you kind of say hello. He's here beside me. I'll scoot over.
Hello, everyone. My name is Sajith Wijesuriya. So I've been at NLR or NREL for now close to 6+ years. My background is mechanical engineering. I did my PhD in the Colorado School of Mines. And then I moved to NLR in 2020. And I've been with the Building Thermal Energy Sciences group, working with several experts on modeling for whole building assessments. So that is sort of my background is mainly on thermal storage integration into current buildings and also looking at the grid interactions and also HVAC systems as well, supporting whole building systems and mostly doing the modeling work at the moment. So that is me. Great to meet you all. I'll be on the background.
All right. He'll be piping in. He ran the Energy Plus models, obviously very intimate with the details and testing parameters. So he's here for questions as well. Okay, I wanted to start by just sharing a slide that was shared with me by one of my clients in Superior, Colorado. This was taken of their house on fire during the Marshall Fire. Sadly, he was in his home with his 2 children when smoke started pouring into the house and was kind of escaped with the help of, first responders and firemen that came on site. He and his family have rebuilt with the blocks that my company makes, and we designed a home for them, and they now feel very protected and more secure from fires. But not only are our buildings susceptible to fires, as we know, we're also running out of sand. If you were to Google sand mafia, there are wars out there. The type of sand that's used to make concrete we're talking about. In fact, the tallest building in Dubai was partially built with sand that was shipped from Australia. So I just wanted to kind of, jump into the showcase of some of the challenges in our built environment today. And again, today we're going to be talking about both sensible thermal mass as it relates to the compressed earth blocks and latent thermal mass as it relates to phase change materials. And again, the company I mentioned makes these blankets. It's a salt hydrate that changes phase and stores energy that way. So as I entered this work with the DOE, I set certain goals with them, and we were looking at really reducing the need for new generation of energy. Of course, we're in this major transition with energy, and it's really reducing the peak demand that will help us um, not need new generation sooner. So this also makes energy more affordable, and then lastly, bringing these new construction materials to market. You know, Todd earlier kind of said that there was once 13 building materials on market, and now there's 13 million. That's probably an accurate. So we just, you know, these thermal mass materials, you know, have a way into the market and kind of showcasing their energy efficiency as well. So just wanted to share a little bit about the work that I do with the clients that come to me that are interested in this building block material. I call them eco blocks, and they are fireproof. I just got a rating from Home Innovation Labs in DC that they are non-combustible. So there is nothing that burns in the composition of sand, clay, and lime and water in the material. They have a longevity to them. People often ask, how long are these buildings going to last? And I say, well, 900 years, 1,000 years, come get me in 900 if I'm wrong. But they really are meant to be a durable, long-lasting building material that we've already seen throughout 10,000 years of history throughout the world. Sustainability, we are doing life cycle assessments, especially when you can source the materials locally and reduce the amount of stabilizer as low as possible, then we're really getting into a sustainable building product. Today, we're going to be talking about the energy efficiency, and again, just that environmental stewardship that I think people come to understanding that this is an eco-friendly product. But on the right, I really wanted to share kind of what they experience, and this is maybe something unique to, you know, building walls that we don't think can be so beautiful and so quiet and comfortable. There's a relative humidity of 45% that's pretty constant in the building, that's optimal for our human health. There's the pH of the blocks resist the growth of mold. And of course, they just feel a greater sense of protection, especially folks who have endured fire or in high wind zones. So back to the model and what we looked at, we took a prototype building from the PNNL website. This is kind of their generic prototype model. Perhaps you've seen it in other models before. And again, we really wanted to isolate just the effectiveness of the thermal mass in the wall. So we left everything else the same, meaning the roof, the windows, orientation, and really just isolated the wall assembly. So the wall assemblies that we use, this is for the baseline and wood frame construction. So again, these are all just code compliant based on 2021 IECC wall assemblies. And so of the 8 zones, we have 7 different assemblies, and this was the cavity or exterior insulation requirements that we got from them. Of course, we're all familiar with the climate zones, and, you know, interestingly, in Colorado, we have 4 climate zones we're dealing with, so quite the challenge here, or opportunity to address a variety. So this slide shows the different wall assemblies that we're working with the blocks the eco blocks. So the slide on the left is just a single wall of just thermal mass. These are typically used for just interior walls. The middle slide is a house in Castle Rock built in 2018. And we put rock wool insulation to the outside of a 10-inch wide earth block. And then, of course, the slide on the right shows mostly what I'm doing now, which is a perlite cavity in two Weiss of earth blocks. I'll mention here that the study in the middle house in the Castle Rock, we did do a study with EMU systems, and where we put data loggers in the wall and exterior and interior temperatures and tracked temperature fluctuations for a year. And EMU Systems wrote a great paper for us about how these walls were really absorbing and releasing energy throughout different times of the year. And purposely, we put a data logger behind their wood burning stove so we could see how it stored, the heat from the fireplace, for over 14 hours or so. So if you go to my website, I can kind of share a link with you of where that paper is.
Lisa, Tobias had a question regarding the perlite technique. Is rebar bridging the perlite layer?
No, rebar, if you see on the left, there's holes in the bricks. So, which are kind of covered up here in the top of this photo. But any vertical reinforcing or all thread and couplers will be coming through the holes in the bricks. The 3-inch cavity of the perlite is purely for the perlite. So it's a continuous kind of insulation layer there in the cavity. We do have what's called DuraWall, which is like a very thin ladder that holds the two withes together, that's placed in the mortar joint every 4th course. And again, it's just a very thin wire that's acting kind of as a girdle for those two block withes. And of course, any reinforcing or engineer will be done by the engineer based on wind loads is our primary issue here in Colorado compared to seismic. Yeah, good question. So I just wanted to share like some of our projects. We just finished this one on the left in Longmont, Colorado. It did win an award in the Green Builder Media recently. If you saw their January-February issue, Alternative Home of the Year. And then phase change material blankets that are being installed in roof assemblies, attics, any sunlit area to again increase the thermal storage of the building. Okay, I'm just going to give a 101 on PCMs and then we'll get into the results of the study. So as I entered this work and learning about phase change materials, water is a really simple one to understand. It goes from solid, liquid to gas, and it takes about 1 BTU of energy to raise water 1 degree. And but something kind of magical in a way happens as it's changing at phase. It takes 970 BTU per pounds to actually break apart the molecules and become a gas. So maybe this is why a watch pot never boils. But again, something is really happening there when it changes its phase, and we can utilize that science in our building envelope to store energy, and while it's storing, it's changing that phase of this material. All right, this is where I'll shift it over to Sajith, who will describe the PCM in particular that was used for our study.
Hello, everyone. So yeah, the objective of the study was to implement the CEBs along with the insulation options that Lisa mentioned, and at the same time compare the performance with PCMs as well. That way we look at the sensible and latent heat. So we did test some of the PCMs that we had, and considering the sort of the complex behavior like hysteresis and subcooling of PCMs, we decided to go with a more close to ideal PCM, which is sort of an average of the current market PCM properties, around 200 kilojoules per kilogram latent heat, and around CP of 2500 2200 range. So this is the sort of the thermal behavior, enthalpy, temperature behavior of that PCM that we used, which has around like 4 Celsius phase change interval. And of course, we fine-tuned in our modeling what is the best temperature range of melting and freezing for the PCM when we were implementing it in the modeling. So in all, we considered 6 wall assembly types. The first one was the standard cavity insulation prototype wall that comes with for every climate zone in the prototype models. And then B is just including the PCM behind the drywall of that prototype cavity wall, which tests the latent heat of the PCM. And then C, D, E, F integrates now the CEBs into this mix. And the first one is that we directly investigated CEB with just the lime plaster layers at the either side without insulation integration. And then we did D, which is the insulation in the form of continuous insulation in the exterior side. And then also E shows the perlite cavity insulation included in the middle. And then finally, the F shows that continuous insulation also with the PCM layer included as well, that combines CEB and the PCMs together. But what we considered in the figures A, B, D, E, F is that you can see that we use insulation in different forms, but we ensured that entire wall assembly at the end of the day, including the other material layers, insulation and CEB, comes up to a equal whole R value in terms of the wall assembly, so that we can compare the impact of the sensible and latent heat, sort of isolate that positive impact in our when we observe the results. So that is something we wanted to note. So in all, we investigated 8 climate zones, selected the representative cities or locations, so that we went through one by one, modeling each of these wall assemblies. So that is sort of the baseline modeling approach. And then later on in the study, we investigated up to, I think, 68 different cities and locations as well. But I will sort of focus on these 8 locations so that we have a sort of a very concise and more visible comparison between the climate zones as well. So first thing that we will look at is the profile of the HVAC electricity throughout the day. So we have selected 2 locations. One is Miami and one is Golden. Miami is from climate zone 1A, and Golden is from climate zone 5. So just to look at the differences between the HVAC electricity profile, to see how different wall assemblies change that and what are the benefits that we see. So on the Miami side, on the left, you can see that this is the middle of the summer, so it's cooling electricity. We have a heat pump assumed in this building model. So you can see that the power demand is higher for the Miami weather than Colorado or Golden, obviously. So, and in terms of the profiles, you can see that the baseline is basically the cavity prototype building. And you can see the fluctuations are a little bit high on that line. And when we start to implement different solutions, starting with CEB, you can see the impact of mitigation of the demand, or the fluctuations are reducing. And CEB alone shows that mitigation of fluctuation, but the magnitude is a little bit high without the insulation. So when we also integrate the insulation, either mineral wool on the exterior or perlite in the center, you can see that the fluctuation reduces, and at the same time, the magnitude also comes down. So that's the dual effect of thermal storage as well as insulation. So together they provide efficient solution, I would say, to motivate or lead to those energy savings and demand reductions. So in Golden, however, you can still see that reduction, but it's not as much as in the extreme or high temperature situation that we see in Miami. So that these are reflected in our annual summations as well. But we just wanted to look at the profiles here just to show how where these savings come from in each season. So this shows the summer, 2 days in July, and then we look at 2 days in February. But now looking at the heating electricity for the heat pump, so Miami, of course, has very little heating or HVAC need um, during the summer. During the winter time or early February, its HVAC need is very minimal. There's a little bit of cooling coming into play, but it's not so much as well. You can see that little bit of a cooling coming into play, but with the solutions that we implement when CEB and insulation comes in, that sort of demand goes away almost. And when we are looking at Golden, you can see that now the power is actually this summer days should be corrected to winter days. I apologize. So this is still the February 2 days. Now the demand is driven by the heating for HVAC in Golden, and you can see that the impact of CEB uh, is observed, but not as much as reducing that cooling that we saw in the Miami during summer days. So we can expect to see a lot of savings from CEBs coming from the reduction of demand for cooling electricity, so which will be reflected in our next results as well. So this is just a sort of a demonstration of the impact of both the CEB and insulation combined solutions in different seasons as well as in different climate zones. And with that, now we looked at the profiles, and now we
If I
go
could
on
interrupt
to.
you briefly.
Sorry.
May I interrupt you briefly? There's a few
Yeah.
questions that I think are relevant to kind of where we're at right now. I wanted to kind of broach them, and if they're coming later in the presentation, you can address them then. But the first is from Yusuf, and he's interested in knowing how the material performs in hot, dry weather. Did you model it in hot, dry climates like Tucson, Arizona as well?
Yeah, I think it's in the next slide where I think we selected one from 2B. Let me just check which location it was. We did Phoenix, Arizona for 2. The 2B is in there.
Excellent. The next question was from Jason, and he was wondering, when modeling the phase change blankets in the wall, how much effect variation did you see based on orientation? Meaning, did you find a greater effect for southern orientation on solar walls or northern air temperature modulated walls? Was that, did you see any difference there?
I think we didn't really explore the structural features. In this model, we assume that the PCM solution or the PCM mat is applied to all of the 4 sides. And I think we discussed this matter as well. So we didn't really investigate into which surface sort of was driving the most impact into the savings that we see. Because you can obviously the southern face heats up more, and therefore the temperature range that southern face goes through is different to the north, and that would impact the melting of freezing or full cycling of the PCM. But at the moment, the results are sort of averaged out because we can consider the holistic effect. But when we are looking at, like, say, if we look at the melting cycle or pattern of each wall, we would definitely see that sometimes in the southern walls in the summer, the PCM would stay melted most of the time and would not fully freeze if the southern wall temperature is very high. So those kind of complexities we of course observe out of the Energy Plus model, but it's not really specifically quantified at the moment. We look at the holistic HVAC energy saving, HVAC electricity saving in this sort of demonstration.
Excellent. Another question we had was in regards to the Miami graph you had. In Miami summer, it seems like continuous insulation is more effective than the perlite cavity. Is this due to the humidity, do you think?
I in Energy Plus, humidity impact is not really fully captured, I would say. This is more a reflection of how the thermal storage and the insulation interact with each other. So I think the fact that insulation is outside may help retaining some of the cold or chill effect or in within the thermal storage for a while than it would if the thermal storage was exposed to the outside, which was my thinking why there is a little bit more retention of cooling and therefore leading to some of the cooling HVAC energy savings that we see when compared to that. I think you can clearly see it in this plot that when continuous insulation, yes, there is a little bit more total HVAC energy saving, which is correct. And I think that was the reason that we thought of.
Okay, excellent. Well, yeah, I think well, let's continue a little bit and we'll pick up some of the questions that dropped in kind of in the interim. So thank you for addressing those.
Yeah, no worries. So now you can see that we come to this 8 climate zone depiction of the results with CEB and CEB plus perlite and CEB plus mineral wool continuous insulation. You can see the CEB alone wouldn't really support because of the missing factor of insulation. Especially the heating impact is felt when there is no insulation. Heating demand goes up. Because of that, the total electricity HVAC goes up. But when we are matching that insulation and when we integrate our thermal storage, we get like close to 10% almost savings in terms of annual HVAC electricity. And you can see that CEB plus continuous insulation is relatively performing better in warmer climates, giving a little bit more HVAC energy savings, like you pointed out in your question as well. And when the climate goes colder, there is a more or less difference we would see in the two insulation types. So that has been our observation through looking at the total HVAC electricity consumption during the year. And similarly, once we look at the total HVAC energy electricity value as well as what is the maximum hourly demand as well observed throughout the year, how much of a reduction that the thermal storage methods would cause. So when looking at that, we also bring in now PCM scenario. So in addition to the CEB, the mineral wool, you can see in the last case, we add a little bit of our PCM layer behind the lime plaster layer on the inside. So with the integration of that additional thermal energy storage, we see that there is a little bit more addition to that peak reduction, because now we have further strengthened that storage effect from both sensible and latent. And the important factor is the PCM layer is just a 1/4 inch, very thin layer. So it doesn't add a lot of thickness to the wall, existing mass wall, which can be attractive. And then we can see a little bit more further mitigation of that demand. So you can see, of course, as the year or climate zone progresses, there's a high heating demand. So that's why the column heights are going up. But you can see when you're looking at 1A, there is a significant reduction in terms of percentage as well when it comes to the combined solution. So these are some of the interesting features of this CEB insulation and latent heat combined solutions. If you look at we can identify which climate zones are attractive to these solutions. So As I said, the continuation of the study was to map it across the United States, that we can visualize it in a more holistic manner as well. And with that, I think I have the conclusion side next. So if we have more questions, we can take up.
Okay, excellent. Yeah, let's pick up a couple questions here. Scott had a question. PCMs were all the rage about 15 years ago, and then it seemed to drop out. They seemed to drop out of contention. Um, what do you think the explanations are? He was wondering, is it difficult to model these using edge components and others, or what are your thoughts on why PCMs may have fallen out of favor during that period?
Yeah, I think the PCMs are still investigated in different modes. But one of the challenges, this is outside little, some of my observations, personally, I would say, is that it's difficult to run it through a full cycling when you are applying it in a passive manner in a existing building, because more or less the interior side of the building is kept at a temperature set point, which is desired for human comfort. So because of that, the thermal cycling of a passive PCM layer towards the inside is kind of difficult, which is how we don't see that input and output of heat into and out of the PCM layer. And when we apply it in on the outside, the tricky part is like sometimes the PCMs can remain fully melted for most of the time because of the higher warmth on the outside. And even if we use the night cooling for solidifying on the outside, still because of that thick insulation there in the middle, we might not get the full benefits into the interior side of things. So these are sort of challenges of, I would say, geometrical implementation for passive PCMs, I would say. So because of that, I think there are a lot of investigations into active implementation as well, which has been going on for a while as well. But these were the sort of the practical challenges we observed in our on-ground field investigations over the last 2 to 4 years, I would say.
Okay. Let's see here. In the total HVAC, which I believe was the previous slide, it looked like the CEB plus PCI MWCI wasn't included in that one. Was there a specific reason that
Um,
combination wasn't included?
I do have the plot for total HVAC energy as well with the PCMs. I think we selected from multiple plots that we had. This one I wanted to sort of just look at the ones without the PCM, but we did have the PCMs included total HVAC electricity plot as well, which also showed some additional savings benefits, just like in the demand side for the PCM addition, in addition to the mineral wool and CB. So there was additional benefits of total savings as well, but not as much as the demand. I should point out. So PCMs are, because of the complex nature of capturing that melting temperature range, sometimes annual energy savings are not really observed, although there are instantaneous demand reductions when the temperatures are extreme, uh, but not really percentage wise or magnitude wise translated into the annual energy savings, which we have observed over the last 2 decades of studies. So that is why PCMs are more um, oriented towards peak demand reduction, sometimes with pre-cooling and preheating. Um, so yeah, but we did have that result as well. Just we didn't transition it into the slides, I would say.
Okay, great. Let's see here. Robin had a question. what are the details of the PCM? Are you guys studying the kind of carbon, embodied carbon in it, embodied energy? Are there petrochemicals in it?
Not at the moment. On the PCM side, because our main focus on was the CEB in this study, we just referred to literature and past studies in capturing the PCM properties, but didn't really investigate into the material side of the PCMs.
Okay, great. I'll let you continue and then we'll pick up some more. I know you have more presentation here.
I just have the conclusion side. I can switch to Lisa as well. So
Mm.
it's just a summation.
Yeah. So I think the takeaway for us was that thermal mass of the earth blocks alone is not a great solution, and the addition of insulation is kind of a must in almost all climate zones all the time. So and we see the most benefits, of course, like throughout the southeastern regions of the state. Our paper does kind of have another diagram of where we're seeing the most benefits, which does seem to be in the southern part of the U.S. throughout throughout the southeast and even in the west also. And I think that we're also seeing a reduction in the demand and the shifting the peak demand, and that was, of course, one of our assumptions. What was interesting to me was the kind of the difference between the insulation to the outside versus insulation in the cavity. I think the graphs show that while there might be slight differences with one in the colder climate zones, the insulation in the cavity seems to perform a little bit better than insulation to the outside, although they're pretty, neck to neck with each other with regards to performance. So some of the next steps for us, I think Sajith had run a model which we can share the results of, but like, what is a power outage? What does a heat wave scenario look like? How do these walls, kind of sustain us in those kind of extreme temperatures? So we will kind of be diving a little bit more into that. And, I did raise the question to Sajith and another scientist here about, high insulation and how these walls with thermal mass compare to like a high insulation, like passive house type wall. And the model will suggest that in hot climates that there's a reduction in performance compared to thermal mass. So again, back to thermal mass being of benefit in hotter climates. So I think that was some good takeaways from us, because I'm just looking back at some notes here. Mainly because the insulation doesn't take advantage of the diurnal effects where we have temperature swings happening, and again the mass can absorb that and equalize that. I did also want to kind of share again that study with EMU Systems, which was interesting because it was an actual home, with actual data and loggers that was in the building, which again showed the swings of our temperatures and more of a flat line house, internal temperature of 68 degrees with no, heating or cooling, mechanical heating or cooling, really just the wood burning fireplace doing the majority of the work for them in the winter. So yeah, it's been really exciting to kind of explore this together, and thanks for the great questions. I think we'll be kind of including some of that, but if there was any other final takeaways, one of the benefits I mentioned at the beginning is fires, and I think that we are just seeing so much of that throughout the US, and with this hot warm winter and potentially hot summer coming again and dry conditions, I think really highlighting some of the fire resistance capacity of these walls. We have a house going up right now in Ward, Colorado, in the mountains. So again, gives people peace of mind, and hopefully a reduction in insurance costs and things like that to boot. So yeah, any other questions, Tyler?
Yeah, we had a few. We'll try and pick up as many as we can before we run out of time here. Thanks so much for that. let's see. Jamie was interested in how the results were modeled versus empirical tests. Are passive solar heating, cooling being factored? And are the weather patterns being modeled versus average weather models?
I can let
I guess
Sajith,
one basic question for me is
yeah,
what is this what is the methodology of modeling in kind of the nitty-gritty sense?
yeah, sure. I'll let Sajith kind of chime in.
I think in terms of weather, we use the TMI3 weather files, which sometimes doesn't really reflect some of the extreme scenarios or extreme temperatures as well, which is why I think we are trying to get some visualizations on how it would perform in a heat wave scenario, both without and with outage. And in terms of modeling, we use the Energy Plus whole building modeling program, so which is very comprehensive in a way in terms of integrating different aspects of whole building model. So but several simplifications are, I think, that came up in our discussions as well as in this call as well, is that the features of the building is a little bit simplified in the current prototype model. So we can of course integrate additional features into different surfaces of the building to make it more comprehensive or baseline, but at the moment it's a very simplistic a rectangular shaped residential building that comes with the prototype guidelines, and that way the complexities are kind of reduced, but at the same time it gives the sort of the holistic impact of the different envelope solutions that we implement without being sort of complexed by the other features. Um, so yeah, so I think that is what I can sort of say. But we made the we made the additions to take into account the air leakage impacts of what was observed by the blower door test into the current models. So we tried to incorporate as much as all those features as well. Only another thing is that the humidity impact is, like I said, is not strongly modeled in Energy Plus. There is a sort of a submodel that incorporates humidity or moisture transfer features, but at the moment, if that is included, we cannot at the same time run the PCMs in the model. So that is a sort of a sort of a shortfall in Energy Plus modeling at the moment. But it's a quite comprehensive modeling in terms of it comes down to even wall level considerations of which algorithms are used for to model heat transfer and all. We considered all that, so it better approximates the PCM impact, because it's a little bit complex to capture the phase change in the interval of temperature range that we want the PCM to melt and freeze. So those things are very well approximated, but certain complex nature of PCMs like hysteresis or subcooling, like I said, wasn't considered at the moment. So yeah, those are the sort of the pointers about the current modeling approach that we are taking.
Excellent. Well, I think I'll take one more question here and then apologies if we didn't get to address your question. I'd encourage you to reach out if it's okay with our guests directly to address your questions we didn't get to today. I think one thing folks were interested in is kind of, I think from a passive house perspective, are compressed earth blocks can we call those airtight? Is this an airtight material? And then I assume, there's some sort of water vapor capacity of these things. What are kind of the takeaways or kind of the general advice of using those in terms of, do we categorize them as vapor open or airtight and those types of things, Lisa?
Yeah, great question, Tyler. Thanks for raising that. So Sajith mentioned the blower door test results that we included in the model, and this was from the house, the rebuild in Superior that we did. And we got a blower door test of 0.7 ACH50. And so basically the blocks are vapor open and are 7/8 inch, three coat lime plaster to the exterior and potentially to the interior, depending on how the clients finish it, is our air barrier. So we do not use a vapor barrier. We want the blocks to be open and breathe as well, especially in the lime plaster and that rendering. The rendering adheres directly to the block, so there's no need for mesh or anything of that nature also. So yeah, vapor open, airtight, with the lime plaster being our air barrier.
Excellent.
So,
and is it okay if people reach out to address some of the questions we didn't get to today directly via email?
Please do. Yeah, please do. Yeah, the questions will really help inform, future presentations and the study, as well as what we can further dive into. I think what was interesting to me with the PCM was kind of its active state, and the fact that it really works a lot better when you pre-cool it or preheat it. You kind of get it to that prime temperature so that it's set before that demand time, and so then you can really utilize it. So I think that was for me a takeaway with the PCMs is using it in a more active state than in passive. So pre-cooling, pre-charging it is called, to get it where you want it when you need it.